All right, everybody. Welcome to the second lecture video for Unit 3. Today I want to look at some population growth models to see if we can continue mathematically modeling how populations grow, and this is going to connect directly into the activity we did in class with the seeds of change, looking at fruit seeds and fruit plants covering the earth. So the general rule that we explored in that activity is that when you have abundant resources, the population will grow exponentially. If there is unlimited food or unlimited space, the population, there are no limits on their growth. Great example are oak trees. Every few years they will release a ton of acorns. This is a process some plants do called masting. And the idea is that they will overwhelm the squirrel population. Squirrels can't possibly eat all these acorns, so some of them will survive and grow into trees. But what this means for the squirrels is that they've basically got unlimited food. There's no way they could eat them all. So their population will grow exponentially for some time anyway, not indefinitely. And populations that grow exponentially tend to have a couple things in common. They tend to reproduce early in life. They have short generation times. They can reproduce many times, and they produce many offspring, or what we say is they have a high fecundity or high fertility. They can produce a lot of offspring. What does this sound like to you? Does this sound like a R or a K selected species? Yeah, it's a R selected species, and therefore also a type 3 survivorship curve. Like I said, with abundant resources, these populations can grow exponentially, and we can actually model this. We started to do that in class. If we say that the growth rate of the population as a percentage between 0, or as a decimal between 0 and 1, we represent that with R, we can use the exponential growth equation to predict the population size in a future point in time. And the population growth equation for exponential growth is n sub t is equal to n sub 0 times e to the RT power. N sub t represents the population size at time t, or the final population size. N sub 0 represents the initial population size, or the population at time 0. E is a constant. We can just say it's equal to 2.7, or you can use the button on your calculator. And R is the rate of growth. This is not as a percentage. This is as a decimal, 0.09, 0.34. Don't put it in as a percentage. It should be between 0 and 1. And T is amount of time. This could be months, years, days, doesn't matter. Just pay attention to the units. And interestingly enough, the equation for compound interest is very similar to this one. So let's do some practice. Consider a population of mice that has an initial population size of 20. Their growth rate is 0.2. And I want you to predict the size of the population 5 years from now. Okay, so this is our equation. Let's plug in some numbers. They tell us that the initial population is 20. E is a constant, 2.7. The growth rate is 0.2, and the time is 5 years. So we plug this in. We do some math. 0.2 times 5 is 1. 2.7 to the 1th power is 2.7. 2.7 times 20 is 54. So after 5 years, the population will grow from 20 to 54.4 mice. This is exponential growth, our selected species. Another calculation that we can do is to calculate something called the doubling time. And in order to do this, we need instead to look at the growth rate as a percentage. This is a little tricky. You're going to have to memorize this. So doubling time is an interesting statistic that you can use to look at your bank account or a population. Basically calculate how long will it take for a population to double in size. And what's interesting about this rule is mathematically it works out, makes sense, but intuitively it's kind of odd. You just take the number 70. You'll use the number 70 every single time, and you divide it by the growth rate as a percentage, and you get the amount of time it takes to double. You don't need the initial population size because the growth rate or the doubling time is independent of the population size. Whether you're going from 2 to 4 or 2,000 to 4,000, doubling time, it would be the same. So let's do an example. The squirrel population in my backyard grows at a rate of 10% per year. What's the doubling time? Pretty simple. 70 divided by 10 is 7 years. It will take 7 years for this population to double. Now, obviously, there are limits to this model, right? Just like all models. All models have flaws. They all make assumptions, but they can tell us something. Limiting factors will change. Population growth rates will change each year. Availability of food and space and light, nutrients, etc. will change. So this isn't perfect, but it is a useful mathematical tool. Let's do some more practice. Mr. Pentakill has $12K in loans. the rate of interest on student loans is 7% per year. How many years will it take for his loans to double? Okay, in part 2, Betsy DeVos wants to raise the student interest rate to 9% if she succeeds. How long would it then take for Mr. P's debt to double? All right, so for this one, you take 70, you divide it by 7%, you get 10 years. It would take 10 years for my loans to go from 12K to 24K. If she raises the student loan interest rate, we do 70 divided by 9%, it would only take 7.7 years for my loans to double, which is pretty substantial. So please don't raise the interest rate, please, thank you. Now, all this time we've been operating under the assumption that populations have abundant resources, but the truth is that's not the case. And this guy, Thomas Malthus, in the 1700s was asking, well, can we grow indefinitely? And his basic answer was no, we're screwed. There are limited resources on the planet, food, water, space, medicine, etc. And he argued that if we don't control our population and the rate at which we grow, we will run out of resources, and as a result, we will experience some significant issues. This is an example of his Malthusian Theory. A population is growing exponentially, but our food resources are growing linearly. So at a certain point, the population growth of humans is going to outpace food production. And at this critical point here is where our population exceeds that. So there, we're going to experience increased mortality and decreased birth rates due to war, disease, famine, pestilence, etc. It's kind of scary to think about, but there is some truth and some over-exaggeration in that statement. So, like Malthus was saying, no population can grow forever, whether that's humans or otherwise, because of limiting factors. These are factors in the environment that are going to prevent the population from growing past a certain point or distributing past a certain point. They include things like light, water, space, predation, competition, and also food. Here, light and predation, you can see there. There are some important iconic limiting factors that you should know. In soil, the three basic limiting factors for plants are nitrogen, phosphorus, and potassium. NPK, as we call it. These are the three main components of fertilizer and are limiting factors in soil. In marine ecosystems or open ocean, the main limiting factor is nitrogen. And the way I like to remember this is that the chemical symbol for salt is NaCl, and in salt water, nitrogen is limited. So I remember because they both have N's in their name. On the flip side of that, freshwater ecosystems tend to be limited by phosphorus. Phosphorus is limited in lakes, rivers, streams, etc. The way I remember this is the sound of the F. Freshwater is limited by phosphorus. Phosphorus doesn't have an F in it, but it makes the same sound, so it works. And lastly, estuaries, areas where freshwater runs into marine ecosystems. We've got freshwater and saltwater, so the limiting factor there is going to be salinity. But when do these limiting factors kick in? If we think about Malthus's theory, at what point does the lack of food start to really impact the population growth? Because if we go back and we look at this graph that he put here, right, the population growth doesn't change, right? It's still going exponentially. That doesn't make sense. So at what point are these limiting factors actually going to kick in and start to slow or even stop the population growth? And we can explore this by thinking about a term called the carrying capacity, which is basically the environment's max load. At a certain point, the environment only has so much food, so much space, so much nutrients and water to support so many individuals. And we can look at that on a graph with a dotted line. We usually represent it with the letter K. Here we've got time in hours on the x-axis and number of yeast cells on the y-axis, and you can see that as the population grows, it starts exponentially, but as it approaches the carrying capacity, the max load of the environment, the growth rate is going to slow. And this carrying capacity is determined by two factors. One, the environmental resistance, the limiting factors that we just talked about, space, food, etc., but also the biotic potential, which is basically the steepest slope on this graph, that under ideal conditions, what is the fastest rate that the population could grow? And that's the steepest slope on this graph. It's important for you to know that the carrying capacity can change. It's not a hard and fast number that is going to stay the same every single year, because these factors that limit growth are going to change as well. The amount of space that's available, the amount of food that's available, and as a result, the carrying capacity can change every month, every day, every year, etc. Additionally, As the population approaches the carrying capacity, look at the slope of the line. It's very, very steep and very positive. It's a very high slope, but the slope starts to decrease, becomes less and less positive. The growth rate is decreasing as it approaches carrying capacity because those limiting factors start to kick in. The resources are becoming more scarce. Competition is increasing. So at this point, what is happening to mortality? Yeah, as a population approaches carrying capacity, mortality is going to increase. More individuals are going to start dying because of competition. What about fecundity? And remember that fecundity is basically how many babies an individual can produce. What's going to happen to fecundity as we approach the carrying capacity? Yes, that's also going to decrease because, again, of competition. But we'll explore in a bit. What happens if these two metrics don't decrease? What if they don't start dying, and they don't stop having babies? What's going to happen then? But first, this is the same graph, right? Before we were talking about an exponential growth where it goes straight up like a J, but when we start integrating the carrying capacity into this model, we can look at it as logistic growth or an S-curve, right? At first, it's exponential, and we have that biotic potential here, the point of maximum growth, but as the limiting factors kick in and as we approach the carrying capacity, the growth rate is going to slow down. Like I said, what happens if it doesn't slow down, though? What happens if they don't start dying and they don't stop having babies? Well, the population is going to overshoot. They've got abundant resources, they're growing exponentially, everything's going great, and maybe they're growing so fast that they burst right through the carrying capacity, and they overshoot. Suddenly, there's more individuals than can be supported by the environment, severe resource depletion, and you see a significant dieback. Sometimes that dieback can bounce back and it leads to an oscillation depending on how resilient the ecosystem is, but sometimes it can lead to a total crash where the population way over exceeds the carrying capacity and then crashes extremely fast and the population cannot recover. So carrying capacity is a pretty important term in ecology. It's something that's hard to calculate and something that oftentimes you can only calculate retroactively by looking at the data afterwards and saying, oh, well, this looks like it's the carrying capacity based on the data we've got. And like I said, it can change year to year, so please keep that in mind.